The Earth's mass is approximately 6 times 10 to the 24th kilograms. But have you ever wondered how we discovered this number? How can we calculate the mass of a planet? The answer lies in Newton's universal law of gravitation, and in this video, we'll explore exactly how it works. So what is gravity? Gravity is the attractive force that acts between any two masses in the universe. For instance, the Earth has a mass, and so does an apple. Although these drawings are not to scale, since both objects have mass, they exert a gravitational pull on each other. This is the force of gravity, but keep in mind that the Earth isn't the only one pulling the apple. The apple also pulls back on the Earth with an equal and opposite force, as described by Newton's third law. Interestingly, this gravitational force is not unique to Earth and the apple. Any two masses in the universe will attract each other. For example, you and the moon, or even you and an apple, exert gravitational forces on each other because of your masses. However, you might wonder, if gravity acts between all objects, why don't we feel this force between, say, furniture in a room? Or why don't everyday objects just stick to each other? The answer lies in the relative weakness of gravitational forces between small masses compared to the overwhelming gravitational pull of the Earth. To understand this better, we need to analyze gravity in more detail. Let's begin with a simple example: the Earth and an apple. What happens to the gravitational force if the mass of either the Earth or the apple increases? Since gravity depends on mass, increasing either mass will result in a stronger gravitational force. This means that gravity is directly proportional to the masses involved. Next, let's consider distance. What happens if the Earth and the apple are farther apart? Intuitively, the gravitational force becomes weaker with increasing distance. In fact, the force is inversely proportional to the square of the distance between the objects. This is why we don't feel the gravitational pull of distant stars or galaxies. They're simply too far away. Newton used observations of planetary motion to derive a formula for gravitational force. The formula involves the masses of the two objects, let's call them m1 and m2, and the distance r between their centers. The gravitational force is calculated as F equals g times the product of m1 and m2 divided by r squared. Here, g is a constant called the universal gravitational constant. Its value is approximately 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, and it was determined experimentally. The tiny value of g explains why gravitational forces between small objects are negligible in daily life. The formula also explains why we primarily feel Earth's gravity. Earth's mass is enormous, about 6 times 10 to the 24th kilograms, and we are very close to its surface. For practical purposes, when dealing with objects near Earth's surface, we simplify the equation by replacing r with Earth's radius and combining constants into a single value. G approximately equals 9.81 meters per second squared. This g represents the acceleration due to gravity near Earth's surface. Finally, using the known values of g, Earth's radius, and the gravitational constant g, scientists were able to calculate Earth's mass. Isn't that incredible? But this method doesn't just apply to Earth. It can be used to estimate the masses of other celestial objects as well.